So I'm from Heidelberg. Well, at the moment, I did my PhD in this beautiful place, so it's always good to come back. Also I'm gonna go old-fashioned. Adam is going to go like really modern side. But so this the talk, the title is status of cosmology. One. So I should basically before I start just mention a few.
Again.
Press it again.
Right.
You need to press twice. Once again, then again.
Thank you. So before I start, just a few points. So first of all, I should thank my amazing collaborators. So many, but I'll try to just thank them. This definitely is great work by all of them. Many of them are in this room. So Adam, Marit Stansa, Edward Morsel, Jonas Sinander, David Mota, who's not here, Frank Connie, over there, Luca Mendola, at the moment in Heidelberg, Marielle Mota, Mali Renebi, Henrik Narcissian, and also there will be, well, there are a lot of like new people, like new blood. So Miguel, where is Miguel? Over there, Matteo Martinelli, Valerio Petronio, or hopefully in the future, Agnes, Philip Gold, Nima Hossein over there. Anyway, so, and this talk is not based on only our works, but I should really apologize in the beginning, so if I don't really mention all the works, it's great work of everybody here, so really, it was fantastic. So I'll try to just basically be quick, hopefully. So that's one point. The other point is that there will be no formulas here. All the formulas will be in Adam's talk. So I basically try to give an overview of the field of cosmology of bimetric gravity. No massive gravity, apologies for that, but I mean that's great truth. But this will be just about bimetric gravity. What I really want from this talk is basically I'm just asking you guys to tell us what to do next, because we are kind of in a crisis now, so it's very important. Okay, then let's get started. So what we have here, start with, I should actually be careful to choose the way. Right, so for the theory of massive, I call it massive by gravity, all we know, basically we have an action, Einstein-Hilbert term for G-metric, Einstein-Hilbert term for F-metric, we have interaction term, and we have in the standard picture matter Lagrangian coupled over to G, right? This is the standard original version of it. We have a lot of like 5 parameters in these interaction terms. We show them by beta I. So you have this action. Of course, from this you can get field equations and some Yankee constants. Well, this is just basically a theory. So when you want to do cosmology, well, the first obvious way is to extract, basically to derive FLRW backgrounds. That's a natural thing to do to start with for both G and F, right? This has been done again, should mention, by many people, including a lot of people in this room. So different works, but I mean this has been shown that was shown basically right after the theory was proposed. This exists, so we can actually do really background cosmology. One thing that one can do with this then is to actually, for example, assume that this beta naught which is, these are actually 5 parameters. Beta naught corresponds to the cosmological constant term for the geometry. So if you assume that that is 0, because that is the quantity that actually receives quantum corrections from matter loops. So let's assume that that's 0, and then you want to know if you can get any self-acceleration solutions with that. So you can actually assume this one. So by self-acceleration here, I really mean this one. So acceleration for beta not equals 0. So for example, we did, I mean, again, together with other people, but I mean, we basically did, it was one of the first things that we did. We compared this theory to observation. So basically trying to observation. To see if this model can actually explain the background cosmology. For example, what you see is like self-acceleration without really including any beta naught term. And then you can see that, yes, you can put constant on the parameters, and that's fine. From here, you can exclude some of the models, some of the sub-models of the theory. So basically, that was nice. So I would say this actually worked very, very right. Well. So this was fine.
Sorry, what do you mean that the other terms don't get corrections from only this one?
Well, no. The thing is that this beta naught is basically cosmological constant vacuum energy that comes from this term. That actually appears exactly like beta naught in the Lagrange. So that's like cosmological constant term for us. I mean, it's not like cosmological constant necessarily at the level of the Friedmann equation, but that's the one that receives directly quantum corrections. That's what I'm saying. I mean, the other matter, well, yeah. So that is an assumption that we can make. Right, so now you want to go further, see what you can do with basically perturbations. So I'll try to do the perturbation part here, or maybe like this. All right, so I put it this way. Basically, you go from here, there. So, if you look at the solutions at the background level, you will see that you have usually basically like 2 branches in the theory, right? So these branches are defined based on a quantity, some people call it Y, some people R, or different notations. This is basically just the ratio of the scale factors of the 2 metrics, right? Depending on how this thing behaves, you can define 2 branches. This quantity either starts with a really large value at early times and then goes to something small, like some finite value late times. These things we call basically infinite branch by gravity. Just a name. The other branch is actually finite branch. This quantity starts from like something really small at early times and then grows with time. So, for that reason,
you assume that the solution matrix are by diagonal both.
what?
You assume that they're both diagonal.
Exactly, that's what I'm saying. For the moment, I'm going this direction. This is FRW solution for both. I'll come back to that. Definitely. I mean, this is just FRW for both of them. So, for the infinite branch here, well, we just called it IBB, infinite branch by gravity. So, and you can show that you can get this one when you have, you let beta 1 and beta 4 non-zero in the field. Otherwise, you don't get this branch. So, this is one of the branches. The other branches are here, are the finite branches. This one actually, for example, includes the theory like only if you only let beta 1, which is the linear fraction term, to be non-zero, you can get these kind of branches, also with other combinations. So these are like basically, it covers a larger fraction of the parameter space compared to this one.
Sorry, Yashar?
Yep.
These are the 2 dynamical branches now?
Yes.
So there's also the 3rd branch which is...
Yes, but in the original singly coupled theory, this original theory, the algebraic branch in principle just gives you GR as far as I know. So it doesn't really give you a non-trivial. So that's why we didn't really
But it's strongly coupled.
Sorry?
It's strongly coupled.
Yeah, also.
It's clear. But you have new degrees of freedom.
I see.
They didn't pick, so it's a big apple.
Alright, but this is based on basically this particular dynamical branch. But I'll come back to that when I talk about the doubly coupled phase. Alright, so then you can actually go here. So for finite branches, of course, next step is to do perturbations. Right? You do perturbations, of course, as usual. You get tensors, vectors, and scalars, right, in here. So if you look at the tensor modes, you can show that this is actually fine. So you don't get any instability or something that kind of is like weird here. So tensor modes actually are stable and in principle fine. You also look at things like Higuchi bound. For example, okay, this has been shown also that, well, this is in principle for this branch is fine. For example, this beta 1 model was shown by Andrew and collaborators in the paper, and I think yeah, good. So basically, for example, this is actually I was shown like first time that this was fine in terms of Higuchi bound. And also the other models. For this one, I recommend you who will be here next week to listen to Frank's talk. I guess he will talk about it. I'm not sure, but it's fine to get started.
I'm not in this field at all, but there was a paper this morning, in fact.
Yes.
Your collaborators in Heidelberg.
I will mention that. That's not about this branch. I'll say. So this is in principle fine. So you have tensor modes, okay. You have Higuchi bound, fine. Then the interesting part is basically scalars. If you look at scalars, you will see that unfortunately this theory suffers from gradient instabilities. I just write unstable, but basically by this I mean gradient instability. So that is not good.
What do you mean by Higuchi? I thought the Higuchi bound is the same as the scalar being stable.
No, I didn't say it just means the same thing. There are different things that you want to do. I said that Higuchi bound is okay. You are not violating that in this branch. But then when you look at the scalar perturbations, early times, for example, I mean just like usual perturbation, it's not like there is a ghost here. It's just the physical propagating degrees of freedom. They actually give you instability, cosmological instability.
It's a vacuum. There is a vacuum. There is an exponential instability at every time. Whatever a reasonable equation of state you choose for matter.
It's
So
a
it's not a ghost.
Okay, so by Higuchi you mean that the scalar is ghost, and by unstable you mean...
Yeah, the kinetic term is the right sign, but there's a great instability
Yes.
and some another time.
Exactly. So this is not good. Even if you include beta naught term, because I mean this is, I assume this beta naught equals, because I was only interested in self-acceleration originally. But if you even include beta naught, which is a cosmological constant term, this really does not help. So this is actually something that seems like, yeah, the problem here. So, sorry.
Is that suppressed by the gravitational mass, the instability?
By gravitational mass. No.
It's just in the gradients.
No, yeah.
It's in the gradients where it has.
Yeah, it's bad because it's in the gradient, so I can make the spatial K as large as I want and make the instability as fast as I want. It's worse than a tachyon.
Yes.
So this is great.
The mass drops out with the frequencies.
I mean, you can have, I mean, people could play with when that happens, you can add higher spatial gradient terms in the effective Lagrange and that can resolve it.
So this is not related to the strong coupling?
No, that's not extrapolable.
It's inside your inside the horizon modes.
Yeah.
Propagation speed becomes imaginary.
Exactly. It's like a sound speed.
So basically, you lose control of your perturbation theory very, very quickly.
Yes.
Because it's exponential and it's every time.
That's my actually next point. So one possible, I mean, this is just a speculation, we don't know. one possibility is that if you, because we know that Einstein mechanics at work in this class of theories, so maybe if you basically, let me write down this and I'll, so because of Einstein mechanism, it might be that this, we don't know, this might actually solve the instability problem. See how? The idea is that, for example, you start with every time. Oh God. So basically, the solution that you have here, they become nonlinear. Not necessarily nonlinear, but I mean the higher order terms in the perturbations become important. So maybe because of Einstein, at some time, these things will basically cancel the other ones. So in a way, you really can cancel this effect of instabilities. Maybe. We are not sure, but that's actually an interesting direction. So, but one thing that we need here, we need basically time gradient. Because you know, for Einstein mechanism to work, you basically need this to actually also happen well, this way, not like a spatial, only a spatial gradient. And I should just mention that this is just a heuristic idea. We don't know. So for sure if it works. If it works, then basically you can do, for example, n-body simulations here, and you can basically maybe show that things are fine. So this time, this is an interesting direction in principle. All right. So let me now look at the infinite branches. So for this one, if you do again perturbations, all right, so first look at scalars. Turns out that scalars are okay, so there is no gradient instability here. So this is fine. When this is fine, it means that you can go further. You can, for example, assume things that people do in standard cosmology, like quasi-static approximation, for example, for linear modes. And this is actually fine. You can do this for this one. And for example, you can calculate modified gravity parameters, standard ones, things like modifications to the Newton's constant, or like you can calculate the anisotropic stress and things like that, or basically a modification to Poisson equation, all these quantities, and in principle you can do like forecasts, for example, for things like Euclid, etc. This is something that we showed in the paper. In principle you can do that. But this is actually for sub-horizon modes, and this is assuming the basically linear growth. And of course you have violations, deviations from GR, you can test this with future experiments. But the problem is, oh, another thing that you can do, you can also look at super horizon modes. For example, one thing that one can do, look at the IS of W effect. This is something that we also looked at to see if it's fine or not. In principle, that's fine. People probably should see Jonas' talk next week. I think we'll talk about this one. That's an interesting thing. Also, maybe one can, in principle, do Boltzmann code and like for like CMB analysis. This of course does not think that. But
excuse me, I have a question. But I mean, how can you really look at CMB? I mean, the cutoff with this theory is pretty low. So in principle, you cannot really get to the point where you can tell how your initial conditions are set, because
okay.
There are tensor modes, there are vector modes, and you have to tell how these modes are produced. So
I
it's
agree,
really
initial
beyond
conditions are important. I mean, also there was this paper that I will mention today on the polarization of on CMB. You can really see it in B modes and all this, like basically TT and all that. This has been done, but there's a serious problem. I mean, I'm not suggesting this actually to be done because of this problem. And the problem is, all right. So another thing that just before that, you can in principle do embody here if you want to study small scale nonlinearities here. But the problem is following. First of all, if you look at the Higuchi bound, you see that there is a problem here. So the Higuchi bound is violated in this branch. That's dangerous. To me, it's like more or less like, I would say this branch is dead. So for that reason, you should be careful if you want to do this embody or something, because in principle, you have problems with embody, with Higuchi bound. So, but for this one, we can look at, for example, Lagos et al. There is a paper, they basically talk about Higuchi bound different branches, and they actually showed this one. Also, again, Frank's topic. Also, another problem is in tensors. Well, tensors are not stable.
But they're ghosts. They're ghosts.
They're ghosts. I mean,
It's not gravity
No.
instability.
No.
I mean,
It's a ghost.
For tensor mode.
yeah, it's a ghost.
The coefficient is basically the propagation speed in the second method.
Yeah,
which
basically-
becomes negative.
Yeah, I mean, your infinite branch means that the speed of light in the second sector is negative. So you have two problems. It's a ghost, and then at a certain point, at
Yes.
late time, it's going to get
That's right.
hit a curve to singularity. So it's very difficult.
That's right. That's right. So this has been again shown by, for example, Lagos et al., Cousin et al. Also, there was this paper today on the archive by Luca, Miguel et al. Basically, look at this effect. They have some ideas, but in principle, this is to me also kind of very dangerous. So
what I understand is,
I would call.
sorry, Yashar. What I understand is they're usually interpreting this ghost instability as some classical instability and trying to tame that instability.
Yeah, I think so.
Sorry, the tensors do not have any ghost. What we found is negative friction, and that causes a growing mode.
I mean,
No, it's more than that.
we did
We
the
didn't
full
see it.
calculation. I mean,
I don't know about the scalar sector.
it's just
There might
C
be other
fielder
problems there.
basically is the coefficient.
Yeah, yeah.
Also including beta naught in this case, that will not help. So this is again like I would say, kind of showing that this direction is kind of close. So all right. So let's just this is for this part. So now this is kind of what I just try to discuss it. So let me see. All right. So if this is the standard way, kind of we have problems, then we should go back to the theory, try to do something more. One way is to, for example, look at non-FRW solutions. Things like, for example, solutions like LTB, Lomet, Bianchi. For example, I did great work on that, and also we wrote a paper with Luca Amendola et al. Basically looking at other possibilities. You can, in principle, you have some consistent solutions, but of course, what has to do cosmology with it to see if there is anything interesting coming out here. But this is one direction that kind of things go down. Another, so this is basically looking at different solutions, but it's the same theory. Another way is, so I would go like this way. So, how can I do this?
Can you summarize them?
Yes, I'll try. So one way is to actually look at different couplings to matter. This is, for example, something that we have started with minimally coupled coupling to the same matter. Things like this theory. But this was just, we did it like in cosmology. The good thing is that you get interest in cosmology in principle from this one. For example, you can get exact lambda CDM, you can get stable solutions, and there are some interesting conceptual issues here. But the problem is that it's been shown, again by Claudio and collaborators and some other groups, that there is a ghost here. So this route is actually not really interesting. You can, in principle, minimally couple to different matter species. This has been done by different groups. One interesting one, for example, was by Amir et al. Remember that you get basically large graviton mass. So I think that is basically an interesting built-in principle. Another way was this, of course, interesting case of effective metric. One example, this theory that was suggested by Claudio et al. This theory. The problem with this theory theoretically is that it's like less appealing because quantum corrections now make the mass terms unstable, the same as the cosmological constant term. Also, in principle, this theory is not goes free all the way to Planck mass. But if you assume this one, then you can do background. And you see that you get also interesting cosmology here. For example, you can have some connection to partial massive gravity, or you can have exact lambda CDM solutions. But again, when you do perturbations, I just write perts. So when you do this, there are two branches here, dynamical and algebraic. People have looked at this one, for example, Emir, Lavinia, also Kazuya Koyama. So for the dynamical case, you basically see that there is ghost at late times, and also maybe there are gradient instabilities for vectors. So in principle, that doesn't sound good. For algebraic branch, in principle, that's okay in terms of ghost, if null energy condition is satisfied. But the problem, for example, is that there is no dominant matter coupled to effective metric at early times. So yeah, it's hard actually to really do things here, but well, we don't know. So there might be some other ways here with some new couplings. For example, Lavinia has one interesting example of G effective, which is like G some metrics here with determinant of 1. I mean, also maybe some other solutions. So this is, I think, an interesting field in principle.
Well,
all right. So the last.
If it has any ghost or
sorry.
I mean, you have to see. If
of course. I'm saying that.
Probably
yeah, this is not interesting direction, but yeah, that's in principle fine. So just the last part. So otherwise, one other way, because you don't have any freedom here. So you can of course try to modify the theory. So by the theory, what I mean is to the gravity sector of this theory. The gravity sector of this theory, well, there are some motivations from massive gravity. For example, generalized massive gravity. You can do non-local. You can do, like, for example, f of r, Lorentz, violating massive gravity. You can have, for example, quasi-gigaton, you can have mass varying, and anything you like. Amongst these ones, the one that, to me, personally, looks kind of more interesting is this direction, because you don't introduce new degrees of freedom into your theory. Because otherwise, it's very difficult to know the effects that are coming from this, or from massive gravity, or from this new degree of freedom. All right, so that's one possibility. In principle, this is interesting, again. And maybe the just last one is that, well, you might be able to go to multi-gravity, I don't know. Like introducing, well, it's more or less like the same thing as this one, but just introducing new.
Why are you saying that in the Lorentz evaluating theories you get more degrees of freedom? There are 5, if you like.
You don't get more degrees of freedom.
You get less.
You get less.
You get less, generally.
All right? Or maybe. All right? So I think basically that's the structure that I have here. So, I mean, there are possibilities, but I mean, I don't know. I mean, that's the whole point of this conference, to hopefully know what to do next. But I'll stop here because Adam should continue.